Hey, how's it going, everybody? Alright, we're going to continue talking about radians, arcs, and sectors. In the last video, I focused on radians, and you know what a radian measure is. You know how to change an angle measure from radians to degrees and from degrees to radians. Now we're going to focus on the latter two in this section, arcs and sectors. And what we're going to be doing then is solving problems involving arc length and solving problems involving areas of sectors. Excellent. Well, let's go ahead and look at a couple of formulas that you're going to be using, and I'm going to derive those formulas for you as well. First, I want to talk about arc length, and I want to focus on when arc length is determined when you have a central angle that's measured in radians. Ultimately, that's what this formula would be for, that we're about to derive. Alright, now, whenever we're trying to find the length of an arc, which would be this arc right there, I'm labeling it as L, what we're trying to do is basically figure out a fraction of the circumference of the circle, right? And if I know what fraction of the circle this sector right here contains, then that would tell me what fraction of the circumference this arc length would be. Alright, now if you've worked with arc length in your geometry classes before, here's what you would have done to find the length of an arc. You would have said that the arc length L is equal to whatever fraction of the circle this sector takes up times the circumference of the circle. Alright, and the way you would have determined what fraction of the circle the sector takes up is based on the central angle subtended by that sector. Alright, now let's say that this was 120 degrees, then this arc would take up 1/3 of the circle, right? If this took up 180 degrees, then this arc would take up half the circle, and so forth. And so what you would have done is you would have taken the central angle measure over 360 to tell you what fraction of the circle that arc contains, and then you would have multiplied by the circumference 2 pi r. Okay, but that only works if the central angle measure is measured in degrees. Now, there's nothing wrong with when the angle is measured in degrees and finding the arc length that way, or even taking a radian measure and changing it to degrees and finding the arc length. But it turns out it's much simpler, the formula anyway, to find the length of an arc when the central angle is measured in radians. So here's how that would work. Instead of theta over the central angle over 360 degrees to figure out what fraction of the entire circle the central angle contains, what we're going to do is we're going to use the radian equivalent of 360 degrees. If I want to know what fraction of the entire circle would be contained here whenever this is measured in radians, well, I want to know what fraction of 2 pi that angle contains, right? Because remember, 2 pi radians are equivalent to 360 degrees. So you multiply theta over 2 pi times 2 pi r. Now, very important, this is for when you have a central angle in radian measure. I cannot emphasize that enough. Alright, that's why I've got 360 in one place and 2 pi in another. It's because of whether I'm using degrees or radians. Now, hopefully you can already see something that's kind of nice here with this formula. You notice when you multiply theta over 2 pi times 2 pi r that the 2 pi's are going to cancel out. And then the formula becomes this very, very simple thing. The arc length is just equal to the radius of the circle times the central angle measure theta. R theta. That's how you find the arc length whenever you have a central angle measured in radians. Okay, well, we'll come back. Make sure you've got that formula written down. We'll use it in problems in a moment. I want to talk about area of a sector and radians as well right now. And the idea with an area of a sector is very similar to the idea of arc length. It's just area instead of distance, right? Whenever we're trying to find the area of a sector, we're trying to find the area contained by 2 radii and an arc that subtends a central angle. Okay, and then the area, of course, would be all of this that's inside of that. That's what we'd be trying to find. Now, just like with the previous one, what we're going to do is we're going to measure theta in radians. I'm going to skip the whole degree thing because it's going to be a very similar thought process we're going to go through here. If I wanted to find the area of the sector, well, it's going to be dependent upon what fraction of the circle is contained within that sector. And to figure out what fraction of the circle that sector contains, I want to put my central angle measure over 2 pi radians. And this time, we're going to multiply that by the area of the whole circle, which the area of a circle is pi r squared, right? Now this formula too will simplify a little bit. You notice that the pi in this denominator will cancel with the pi from the pi r squared. And so the formula becomes like this. The area of a sector is r squared times theta, the central angle measured in radians, divided by 2. Always make sure though, if you're using this formula, that the central angle is in radians. Won't work otherwise. Alright, well let's use these two formulas. You've got them written down, don't you? Good. First, I want you to find the length of the arc that subtends a central angle of 2.8 radians in a circle with diameter 16 centimeters. Now this problem, if you use a formula, you might get away without using a picture here, but I'm going to suggest that we draw a picture. So let's go ahead and do that. Let's draw a circle. So there's my center and so forth. Now, bonus points from me if you can kind of draw this to scale without my instructions, all right? And what I'm referring to is the angle measure here in radians. 2.8 radians, do you have an approximation of how much of the circle that would be in your head? Well, remember there's there's about 6.28 radians in total since there's 2 pi radians in a circle. So that would be for 360 degrees. 180 degrees would be about 3.14 radians, wouldn't it? So 2.8 radians is just shy of half the circle. So maybe this could be the central angle measure if the central angle is 2 pi radians. Sorry, 2.8 radians. Okay, now remember that whenever you label an angle and you don't put any units, it's implied that that angle is being measured in radians. If I put I'd have to put a degree symbol if I wanted it to be otherwise. So that's 2.8 radians, and the radius of the circle, 16 centimeters. And we're trying to find the arc length, which you'll typically see designated as L, at least in the formula booklet. That's the way that it's given to you. So that arc length L is going to be equal to the radius times the central angle measure in radians. Well, the central angle is in radians. We don't have to convert it. And we have the radius 16. We're just going to do 16 times 2.8. You don't get a lot simpler than that, do you? And so that comes out to 44.8 exactly. That's not a rounded answer. And the arc length will have the same unit of measure as the radius of the circle did. So in this case, it's going to be centimeters. Very good. Let's try another. This time, we're going to say that an arc RS subtends an angle of 4 radians at the center Q of a circle with radius 2.1 centimeters. Find the area and perimeter of sector RQS. Alright, well, that's more of a mouthful. Let's draw a picture. I doubt you'll get away without drawing the picture on this one. Alright, again, let's see if we can kind of draw the central angle measure as close to scale as we can. 4 radians is going to be more than half the circle, right? Because half the circle would be 3.14 radians. So let's say we got one end of our sector there and the other one there. Now that might look weird, but what we're saying is that this is 4 radians. Okay? And then the radius is 2.1 centimeters. Now I need to label some names here as well. It mentioned that the arc was arc RS. Okay, so let's just say that's point R right there and point S right there. Now there's 2 arc RS's, but we're looking at what's called a major arc RS right here. Okay? Because we're looking at one that's more than half the circle, right? More than 3.14 radians. And then it told us the center of the circle was Q. So let's put point Q right there. Now, to find the area, all right, we got to find area first. We're going to use that area equals r squared theta over 2 formula. So simply we're going to go with 4 squared times the central angle measure, and it's in radians, so that's good. It works for this formula. Divided by 2. And see what that gives you. 16.8 square centimeters is going to be the area of the sector. Alright, now I just want to make sure we're clear about where the sector is. I should have outlined this before. There's our sector, right? And it's bound by all of that. And we found the area inside of the sector. Wish I could do a little light shading here. Let's see what I can do. That's about as light as I can get it. So we just found this measurement right there. The next thing it asks for is the perimeter. Now, I want to emphasize to you that the perimeter of the sector is not just the same thing as the arc length. Certainly the arc length is part of the perimeter, all right, because that's part of the distance around the sector, but the sector is contained by the arc and 2 radii, isn't it? All right, so in order to find the perimeter, what we're going to have to do is find the arc length, which we'll call L, and then we're going to have to add the radius here and the radius there. So, perimeter equals the arc length plus twice the radius. All right, that'll always find you the perimeter of a sector. And the arc length, of course, we're going to use the r theta formula for that. So, simply 2.1 times 4. And then we're going to do plus 2 times 4 for the 2 times the radius. And there's your perimeter. Very similar number to the one we got for area. That's coincidental. 16.4 centimeters is the perimeter of that particular sector. Alright, great. One more problem that we're going to work on where you're trying to do kind of the opposite, where you're given arc length, where you're given the area of a sector, and you're trying to figure out what's the angle at the center and what's the radius of the circle. Now, I just basically explained what the problem is, but let me read the problem. In the circle with center C, the arc TV subtends an angle of theta at the center. We'll draw that in a moment. If the length of arc TV is 21.6 centimeters and the area of sector TCV is 129.6 square centimeters, find theta and the radius of the circle. Alright, draw a picture. It must be done. Now this time we don't know theta, so there's no point in us trying to make the central angle to scale. Let's just go ahead and make some kind of central angle and label it as theta. And it said there's an arc TV, so let's label these points T and V, and the center was called C. Alright, so that's what we know, and it tells us the length of the arc is 21.6 centimeters. Well, so I guess there's a little bit more we know. 21.6 centimeters is the length of this arc right here. And in the area of the sector, this region right here, is 129.6 square centimeters. Okay, so how can we use that information in order to find the radius and radius of the circle and the central angle measure theta? Well, let's take the two things that are given and see how they relate to the radius and theta. Let's go with the arc length first. We know the formula for arc length is that the arc length is equal to radius times theta. Now, we don't know the radius nor do we know theta, so that formula can't help us find either one quite yet. But I can at least write that 21.6 is equal to r theta. Now, secondly, we know that the area formula is r squared theta over 2. Now again, we don't know r or theta, so we're not going to be able to find either one with this formula directly. But what we can do is go ahead and substitute 129.6 in place of a. Alright, now notice we've got two different formulas that have the same two unknowns, r and theta. So essentially all we're going to be doing is solving a system of equations here. And our goal is basically, let's use the substitution method in order to find out r and theta. The easiest way to do that would be to take the arc length equation here and to get either r or theta by itself. What I'm going to choose to do is get r by itself. Okay? No particular reason to pick one over the other. I'm just picking r. and r is equal to 21.6 over theta. And then I can substitute that into the area equation. All right, so 129.6 would equal 21.6 over theta squared times theta over 2. Now, can you see how I did that? I just put the r squared right there, kind of separate. This is r squared, and then I still kept the theta over 2. All right, well, remember before you try to do any canceling here that you've got to square the radius. All right, it kind of looks like the thetas would cancel, but you got to do this radius squared. So we'll get this to begin. 129.6 equals 466.56 over theta squared times theta over 2. All right, now we're going to do some cancellation. We can cancel out this theta with one of these down there, so we're just going to be left with a single theta in that denominator. And that will then give us 129.6 equals, and I'm going to go ahead and do a little bit more canceling. Let's go ahead and divide this by 2. Alright, so that makes that a 1, and that makes this 233.28. Alright. There we go. And now imagine there's a two-step process here. We would have to get the theta out of the denominator, so let's multiply both sides by theta. And then you'd have 129.6 theta equals what's on the other side, so you'd have to divide by 129.6. Your value of theta, let me come over here, is going to end up being equal to 233.28 divided by 129.6. Looks like a horrific number. Let's see. Nope, actually that works out quite well. Our central angle measure is 1.8 radians. Don't have to write RAD, but you're welcome to if you like. So there's one of our answers right there. We found the central angle measure. We still need to go ahead and find out what the radius is, and that's simply done by dividing. Remember our formula right there, or our equation right there. 21.6 by 1.8. That would tell us then that the radius is 12 centimeters. All right, there you go. That's how you use arc length and area of sector formulas. As always, I appreciate you watching. Hope this helps you. See ya.